Welcome back to our Python Quickstart tutorial. In this video, I will demonstrate how to implement the Newton algorithm using while loops. While loops are very useful in applications where we do not know from the beginning how many times we have to go through a loop. We typically have such situations in iterative algorithms where a condition at runtime determines whether or not we have to continue looping or if we reached our goal and can stop at that point. The most common algorithm that we use of this kind is the Newton algorithm for finding the roots of a nonlinear function. I'm going to use this engineering application to show you how to implement that algorithm and to show you where the traps are and how to work around those. And with that engineering application, I want to introduce looping, I want to introduce conditions, I want to introduce functions as argument. And that's the next thing that we have in Python. A variable is a pointer to some data. But if you think a function in that sense is also a type of data, you can use functions as arguments. Let's look at this here. I define a function f here. The function f takes an argument and I put that in a variable x. That variable x, I use this to compute a value. What is that value? Oh, x times x, or x squared minus 3. And I want for a Newton method, I need its slope. So if I take df over dx, that should just be from here. X squared gives 2x, and 3 is a constant, so it's just 3x. And I want this function to return both the value and the slope. So I put those two values into one. What are the parentheses? I return one object, and this object is a tuple, and that tuple has two values. The first is value, the second is derivative. That would be one way of dealing with that. That is my entire function. So this is given x, return the value and the slope. The other thing shall be a function. That's a typical Newton algorithm. So I skip here a little bit through your mathematics course. The Newton algorithm basically says, give me a function and guess where the roots of these functions are. Root is where that function value goes to 0. The Newton algorithm is finding the closest to this x0 position for which the function f of that value is 0, and it shall return that value. So what I'm doing is I start iterating. I preserve this. I don't want to modify it, so I use just x. I have a function. I don't know which function. The algorithm shall work for any function, not just for my x squared minus 3. So any function. So function is just a variable. I could call that y and y, whatever. Just don't call it big F because that's a reserved word now that we named it a function. And when I call that function, I could either use here one variable that has the first entry is the value, the second is the slope, because that's how I return it. Or I define here as well a tuple of the same size as that return value. And that basically says if these are identical, it means the first value is assigned that first value, the second is assigned the second value. That's nice. And I actually make here a nice print statement that tells me a little bit where I am. And now I use another loop. And it says, if for my guess x, my function value is not 0, then we need to perform one correction operation and compute the value, and we will need the slope as well for the next step, and we need to check. So we run that loop until we hit the proper result. And I'm using here, and that's a bit more computer numerics. Computers rarely give you an exact zero. So I say if the absolute value of f, I want where f is 0, I say if this is plus minus 10 to the minus 12, I call this 0. That's good enough for me. That's when I stop. So a while loop is a condition until this thing is done. It reaches that condition, it keeps looping. That's very dangerous in that sense. That's the way to create endless loops. And we talk about that a bit later. But in the end, I use this. So I defined here two functions, the function f and the Newton algorithm. And here I do two different start values. Okay. X squared minus 3 is 0. We know that the solution is plus minus square root of 3. So let's just make guess values, run that operation, and we get our loops. The first one, and you see, I just right away print the result. It returns the solution. We call the Newton algorithm. The argument f is, hey, that's this function f. I can define other functions and call it with a different function, f1, f2, whatever. And that's my start value. If I started, what was my output? I plot x and the value f of x. We start at x is 1, f of x is 2. The Newton algorithm says, hey, jump at 2, f of x went to 1. The next correction puts us to 1.75. Hey, we are down to 0.06 and so forth. And we get down, and eventually after 1, 2, 3, 4, 5 corrections, I end up to drop to machine accuracy. That's about 10 to the minus 16. So I'm below 10 to the minus 12. That loop ended, and that first command printed the result. So all these lines are the print lines within the function, while this is the print of the return value. And then we start with a different one, but with -1. And if you check the result, this is plus square root of 3, and that is minus square root of 3, up to 16-digit accuracy. So what we've done was, I showed you with this example, function definition, functions as argument to functions, while loops, and actually the implementing of the Newton algorithm. So for everybody who is doing some nonlinear analysis class, you will like Python, because from here, this can be expanded with a few lines into multidimensional problems, looking very much alike. What did I get with this example? It was very universal. It showed a lot of things in just a few lines of code. That's really beautiful to get the Newton algorithm done that way. What did I do bad? I mentioned it earlier. While loops. What if you have a programming error and this procedure does not converge? You never get to 10 to the minus 12. This thing's going to run forever. It's never going to stop. And that's the big danger with while loops. And let me close this chapter with a trick. How do I get a while loop to work safely? I call this my emergency exit. If you program a while loop, I highly recommend, before you run that the first time, you program a while loop, think about how to make a safe emergency exit. That means, how do you stop your code from running forever where you don't know, oh, the computer is still busy, or I screwed up. So what I do is I add what I call an emergency counter. It's just a variable outside the loop. Before I go into the loop, I say I count 0. And inside the loop, I add to my normal code. It's the same code otherwise. I say step this by 1. This step one, by the way, is showing us another little Python thing that you may not know from other languages. It's present in C, C++. It's not present in Fortran. It's not present in MATLAB. And that's the plus equal. You may know from MATLAB that you say, oh, count is count plus 1. That's correct, that works, but it's not always the most efficient way. And there are operators plus equal, minus equal, times equal, divide equal that says take myself and add 1. Minus equal says take myself, subtract 1. Times 5 says take myself, multiply myself by 5. That is in the beginning a bit weird to see, but it's actually very efficient. C++, you will see next week, has an even more elegant one for plus or minus 1. So here, this just says add 1 to the counter. So what does that do? The counter says, how many times did I go through this loop? 1, 2, 3, 4, and so forth. And then I say, if my counter goes beyond that limit, I say, you know what, that's an iterative procedure. It should be done within 10 times. If it's not done within 10 times, something is off. Yeah. Or I said, if I've done that more than 6 times and it didn't converge, maybe my derivative is wrong. Maybe I did a programming error. And so now we could use the exit the loop, which we've done. That's the break command. The only thing is, we don't know if it converged or not. If we use break, we say stop the loop, whatever you have by then, and that may be a decent approximation. It may be pretty bad, so we don't know. I do here a different thing. There is the raise command. Raise says trigger a Python error. We make our application crash. I say, if this didn't work, something's wrong, trigger an error. And there are different types of errors, and I just raise runtime error. I recommend, again, look at the manual. This is pages and pages of different error types. An error that you raise is information for yourself on what went wrong. It helps you find your bugs. Always assume something can go wrong and leave a message for yourself. So here, if that counter goes up, I just let the user know failure to converge, something went wrong. That's the only little bit that I change in my loop. So I count how many times I'm in there. And I say, if this exceeds an acceptable number, crash with a nice error message from myself. So how do I test this? I run it here. The first 2 lines is exactly what I've done above, and we needed 6 steps. Now I pick a different start value. And I know that start value is a bad one. So I run this, and let's see what happens. Let's look first at the output. We started +1. It had its iteration exactly as before. We started -1. It took a few steps, and we got somewhere. But now I start at 0.01. And what happens now is, look at the error. The error is going crazy. I'm here at 2,000. I'm at I'm at 22,000. I'm at 5,000. I'm at 1,000. I'm at 350. So it goes slow, and it may eventually get there. But I say, you know what? I don't want to make a performance code that does this. And at that point, I said, this is no longer acceptable. That's when my count went up. I go raise my runtime error, and raising is responsible for that last message. So, right, runtime error. It says we have a runtime error. That runtime error, that's the message. Read the message. And the message says failure to converge. What's the rest telling us? it started in my code. It was this operation. You see where the error is when we had the bad start value. And then in this line, we came to this runtime error. That's where we died. Yeah. So raising things allows me to leave feedback. I say, oops, something goes wrong. I may need to revisit my code. And now imagine you've written a code with 10,000 lines of code, and this just crashes silently or goes in an endless loop, and you don't know where that's going on. Versus a simple thing like this, that once your code's working properly, it should never go there. But if your code has a problem and it goes there, it tells you what went wrong and where did it go wrong. So that little bit of extra coding helps a lot on how to do it. At that point, I'm at the end of my chapter on basic data types. That was a very long chapter. And from here, we're gonna move to more engineering applications, data types that we need for computations.